The big question for this segment is, what happens when living systems break down? When thinking about the complexity of life and the evolution of complex life, we can see that there are quite a few points in the fossil record or the geochemical record where huge changes in the composition of the atmosphere and sediments occurred. We can also see chemical remnants in ancient sediments and gain insights into changes that occurred in the evolutionary history of life on Earth and the evolution of biochemical events or systems. In this lecture, we will look at one evolutionary event where some very complex-looking molecules were utilised by primitive organisms to drastically change the face of the planet. Life evolved on Earth over 3 billion years ago. When we consider early life in the history of the Earth, 2 to 4 billion years ago, we think of simple bacteria with no complex internal structures. These bacteria evolved complex biochemical pathways utilising metal ions and complex cofactors to help them divide and reproduce and utilise chemicals in their environment. The environment includes the atmosphere, the hydrosphere and the lithosphere. They probably had limited resources, simple amino acids, organic acids and metal salts dissolved in the hydrosphere, methane in the atmosphere and solid low solubility salts in the lithosphere. There was no oxygen and the chemical environment was highly reduced. They made use of complex molecular cofactors to drive and catalyse chemical reactions in order to make more complex molecules. So where did these cofactors come from and what do they look like? Vitamin B12, bacteria chlorophyll, heme, and factor 430 are all examples of compounds known as tetrapyrols. Looking at these structures, we can see they look very complex, but they do have some similar features, and they are ideal for coordinating metal ions, which are used in catalysing chemical reactions. These complex molecules also stabilise and often improve the solubility of the metals. Vitamin B12 and factor 430 would have been used very early on in evolutionary terms, and they are used extensively in methane and single carbon metabolism, which would have been some of the earliest biochemical processes. Bacteria chlorophylls and chlorophylls capture light for photosynthesis. Bacteria chlorophylls are more reduced than chlorophyll and are only able to be used in anoxygenic photosynthesis. And it is possible that slightly different types of anoxygenic photosynthesis may have evolved a number of times in the evolutionary history. In contrast, it appears that oxygenic photosynthesis only evolved once and was dependent on using chlorophyll A to work. So oxygenic photosynthesis is dependent on chlorophyll A being synthesized. Surprisingly, tetrapyrols can form spontaneously by acid catalysis from simple precursors, like aminolevulinic acid. So despite appearing to be quite complex, the basic structure can form from simple starting precursors. When we look at these chemicals, we see in their chemical structure how and why they were first utilised. Pyrrols were formed from condensation of some types of amino acids, and tetrapyrols were formed from reaction of these pyrrols, with the 3-isomer being the most abundant. Organisms then evolved to use and further modify these complex tetrapyrols, and they obviously use the ones at the highest concentration. Thus, all biological tetrapyrols now used are derived from the 3-isomer. Because of this, they got locked into using these isomers, so when a biochemical pathway evolved to make them more efficiently, they had to evolve a complex mechanism to make the most common isomer found from spontaneous chemical synthesis. We now see aerobic and anaerobic pathways for these compounds, with the anaerobic pathways being found in more ancient bacteria, while the aerobic pathways are found in some bacteria and higher organisms. It took a long time for photosynthesis and then oxygenic photosynthesis to evolve, talking 1.5 to 2 billion years after life first evolved. But when it did, it caused massive changes in the environment. There was a massive oxidation event as oxygen appeared in the atmosphere about 2 to 2.5 billion years ago, and this was due to oxygenic photosynthesis. Oxygen was a byproduct of photosynthesis and is an extremely toxic gas for organisms growing anaerobically. The gas was initially absorbed chemically, For example, soluble metal salts became oxidized and insoluble, but this buffering was short-lived on the geological timescale, and it lasted only about 100,000 years before significant quantities of oxygen and gas appeared in the atmosphere. Chemical processes in cells were inhibited by oxygen, so new systems had to evolve to cope, or organisms retreated to anaerobic niches. Think dark and deep, away from the oxygen and the oxygen producers. So both of these things disrupted not only the atmosphere, but also had a huge impact on the materials available for primitive bacteria to use. The composition of not only the atmosphere, but also the hydrosphere and part of the lithosphere changed dramatically due to this oxidation. This oxidation event was also the likely evolutionary driver for more complex eukaryotic organisms, which based on the fossil record seem to appear around the same time. These eukaryotes arose due to symbiotic relationships between a primitive anaerobic organism and an aerobic organism, as the aerobic organism had developed mechanisms to detoxify and also utilize the toxic oxygen gas. So while one complex biological system almost vanished as it had to retreat to niches where the oxygen concentration was low, a new complex system evolved to take its place and harnessed the toxic material, which is oxygen gas, to thrive.